Okay, guys, so our last lesson of this chapter, and actually our last lesson of Unit 3, is acid and base strength. Okay, so we're going to be talking about acid-base strength. We're going to be looking at the properties of weak acids and bases compared to stronger acids and bases. We're going to once again talk about what percent ionization is, and then we're going to be looking at something called equilibrium, Ka and Kb, and how that relates to percent ionization. We are going to be calculating the concentration of hydronium ions, concentration of hydroxide ions, and pH using Ka and Kb values, and why it's necessary sometimes to calculate pH that way instead of the way that we learned a couple lessons ago. And then lastly, we're going to talk about what polyprotic acids and bases are and look at all the different ionization reactions that they undergo. So first of all, when it comes to the property of strong versus weak acids are much more common than stronger acids. As far as strong acids go, the most common ones are hydrochloric acid, sulfuric acid, and nitric acid, while weak acids include things like acetic acid, lactic acid, and citric acid, as well as a lot of other everyday kind of products. All acids are conductive to some extent because they will produce ions in solution. They're all electrolytic, but stronger acids will be more conductive than weaker ones. All acids will also react with metals and carbonates, but the reaction will be stronger and faster with stronger acids. Stronger acids will have a lower pH, so closer to 1 than weaker acids. Though again, all acids will be somewhere below 7. And all of this happens because in solution, stronger acids will produce more hydronium ions than a weaker acid would, even if you use the same amount and same concentration of both. Because of the percent ionization, stronger acids will produce more hydronium ions. Again, most bases are weak. It is more common to have a weak base than a strong base. Strong bases usually have an OH at the end of them and a metal like NaOH, and then weak bases often don't have that hydroxide in them like ammonia. All bases will conduct electricity. They will always be electrolytic because they will either dissociate or ionize in solution to produce ions. But again, stronger bases will be more conductive because they will produce more ions in solution. Strong bases will also react more readily than weaker bases, and strong bases will have a higher pH than weaker bases, though they will all be above 7. And in this case, the property comes down to how much hydroxide ion is produced. So stronger bases will produce more hydroxide ion in solution, because again, they will ionize or dissociate more than a weaker base, and therefore the weaker base would produce less hydroxide ion in solution. So when it comes to the strength of an acid or a base, concentration is not the same as strength. Concentration refers to how dilute it is. But just because something is dilute doesn't mean that it is weak. And just because something's really concentrated doesn't mean that it's strong. So concentration is the actual amount of the acid or base that's dissolved in the solution. The strength of the acid or base is just its percent ionization. So an acid is really strong if it ionizes a lot, which means it produces a lot of hydronium ions in solution. A base is really strong if it either dissociates or in some cases ionizes to produce a lot of hydroxide ions in solution. So just a reminder, percent ionization is how much the acid or base ionizes or dissociates when it's in solution. If we're talking about strong acids and bases, they will either completely ionize or almost completely ionize, which means that every single molecule of that acid or base is going to break apart into the ions. So for every molecule of the acid that you started off with, you have a molecule of hydronium ion that's produced, or more than one. If it's like H2SO4 or something like that. When we're dealing with strong bases, those base molecules that start off in solution will completely dissociate. So for every base that you started off with, you will have at least one OH molecule or OH ion that's being produced. Weak acids and bases only partially ionize, which means that if you put that weak acid or base in solution, some of the molecules will break apart into the ions, but many of them will just stay floating around as that complete acid or base compound. And so the ones that don't break apart don't produce any hydronium or hydroxide ions, which is why the concentration of hydroxide or hydronium ions is lower when you have a weak acid or base. So again, stronger acids and bases break apart more and therefore produce more hydronium and hydroxide ions. And then the strength of the acid and base is directly related to the amount of hydronium or hydroxide ions that are produced, which then is directly related to the pH of that acid or base. So strong acids or bases will have close to a 100% ionization. Weak acids and bases will have less than 50% ionization. And so this is where Ka and Kb comes in. So Ka is the measurement of how much an acid ionizes. Kb is the measurement of how much a base ionizes or dissociates. So again, stronger acids and bases will have larger Ka and Kb values. Weaker acids and bases will have lower Ka and Kb values. So both Ka and Kb are types of what's called an equilibrium constant, which is also called the dissociation constant. Essentially, anytime you have an aqueous solution, it is going to reach some type of equilibrium, so some type of balance. We even talked about this happening just with normal dissolving processes, where there's an equilibrium between the rate that a solute is dissolving and the rate that it's crystallizing out. So the same thing will happen with acid and base reactions. So in an acid or base ionization or dissociation reaction, the reaction takes place in both the forward and reverse direction. The forward direction being the one that we write out when we're writing out, say, our ionization reaction, and the backwards or reverse direction just being if you were to read that equation backwards. So for instance, you might have like a chlorine ion reacting with a hydronium ion to make water and hydrochloric acid. That reverse reaction becomes stronger the weaker your acid or base is. In a really strong, with a really strong acid or base, the reaction is going to be almost entirely in the forwards direction. So it's just going to be like all of that acid or base is ionizing or dissociating. It has a really high percent ionization, and therefore it's very strong in the forward direction. If you have a weaker acid or base, it means that there is going to be at least some movement in the reverse direction, where as you are producing hydronium and hydroxide ions, you are also using those ions to create water again. So if you have a lower percent ionization, that means you have a stronger reverse reaction. So if you have a strong acid or base, it's going to produce a lot of either hydronium or hydroxide. It's going to have a very large Ka or Kb, and it's going to be a very strong forward reaction. If you have a weak acid or base, it will have a low percent ionization. It's not going to produce as much hydronium and hydroxide ions. The smaller Ka and Kb value represents that lower percent ionization, and the reaction is going to be stronger in the reverse direction. So these are the three different formulas that we're going to be using when calculating pH with Ka and Kb. First of all, Ka plus Kb will always equal 1 times 10 to the negative 14. But these two formulas underneath are the more common ones, and I'll explain what this all means in a moment. So for Ka, the concentration of hydronium ions times the concentration of the other ion divided by the concentration of the original acid is how you figure out what that equilibrium constant is. And then for bases, your Kb will be equal to the concentration of the hydroxide ion times the concentration of the other ion that's formed divided by the concentration of the base that you started off with. If you're given a Ka or Kb value, then you're going to have to use those formulas to determine the concentration of hydronium or hydroxide ions. And then you can use those to calculate pH or pOH. If you have a weak acid or base, you can't just set up a mole ratio to find the concentration of hydroxide or hydronium ions, because that only works if all of your acid or base is getting converted into the hydroxide or hydronium ions. So you have to assume a high percent ionization to use the calculations that we learned for pH and pOH a few lessons ago. If you have a weaker acid or base, your mole ratio no longer is accurate, because you can't assume with a weak acid or base that all of your acid or base actually gets converted into the hydronium or hydroxide ions. So you can't use the mole ratio with weak acids or bases. That's why you have to use the Ka or Kb value instead in order to calculate your concentration of hydronium and concentration of hydroxide ions. So let's go over an example of how to do this, and then I'll leave the other example for you. Also, sorry, just by the way, this is what I was just talking about. So the reason why we have to use Ka or Kb is, again, because the mole ratio does not work if we have a weak acid or base, because in order for the mole ratio to work, you have to just have a forward reaction. If you have that low percent ionization and the forward reaction isn't as strong as the reverse reaction, then that method that we learned previously isn't going to work. Okay, so you have to use Ka and Kb instead. Okay, let's do an example. Okay, so for this question, it told us what our Ka value was. So that's our dissociation constant, is 1.8 times 10 to the negative 5. It also told us that our solution concentration was 2.3 times 10 to the negative 2 molar. It then asked us to find the concentration of hydronium ions and the pH. So we start with this formula here. So this is our Ka value is equal to the concentration of hydronium ions times the concentration of the other ions divided by the concentration of the acid. So we'll plug in our Ka value of 1.8 times 10 to the negative 5. We'll plug in the concentration of our acid, which is 2.3 times 10 to the negative 2. We don't know what our concentration of hydronium ions is, so we'll put an X there. And we also don't know what our concentration of the other ion is. So I'll put an X there as well. Now for all of the problems that you do in Chem 20, the concentration of hydronium ion will always be equal to the concentration of the other ion. So because of that, we can always write both of these variables as the same thing. So I can write them both as x's. Because of that, I can further simplify by saying x times x is x squared. So if you want to kind of jump right to this step here when doing this problem, you can just write in your Ka or Kb value on the left-hand side, your concentration of your acid or base on the bottom, and then the top will always be x squared. And then to solve for the x squared, I'm going to isolate by multiplying both sides by 2.3 times 10 to the negative 2. That'll cancel out on this side. When I multiply my Ka value by 2.3 times 10 to the negative 2, I get 4.14 times 10 to the negative 7 is equal to x squared. Then in order to get rid of that squared sign, I square root my x, which leaves me with just x. And what I do to one side, I must also do to the other. So I will also square root my 4.14 times 10 to the negative 7, and that leaves me with 0.00643 molar. That is my x value, which is my concentration of hydronium ions. Once I have my concentration of hydronium ions, I can plug it into my pH formula. So pH is still equal to the negative log times the concentration of hydronium ions. So I'll take the negative log of 0.00643, and you should get a pH of 2.19. So try the other question on your own now, and then come back to see the answer. Okay, so this is how you solve the second question. So it gave us our Kb value of 1.7 times 10 to the negative 5. It also gave us our concentration of our base, ammonia, which is 0.01. And then again, I just put my x squared on top. That represents my concentration of hydroxide ion and other ion. So I'm going to start by multiplying both sides by 0.01 in order to isolate the x squared. My Kb times 0.01 is 1.7 times 10 to the negative 7, which is equal to x squared. I then get rid of the squared sign by square rooting, and then because I do it to one side, I must also do it to the other. The square root of 1.7 times 10 to the negative 7 is 0.0004123. Now, because this was a Kb value, what I solved for here was not the concentration of hydronium ions, it was the concentration of hydroxide ions. So make sure you know whether or not you're using a Kb or a Ka. If this is a Ka, your X value will be the concentration of hydronium ions. If it's a Kb, your X value will be the concentration of hydroxide ions. Because it is the concentration of hydroxide ions, I cannot plug it directly into the pH formula. Instead, the easiest thing to do is plug it into the POH formula, which is the negative log of the concentration of hydroxide ions. So I take the negative log of my concentration of hydroxide ions and get my POH of 3.385. And then as my final step to find the pH, I just do 14 minus the POH, so 14 minus 3.385. And I get a final answer of 10.615. When we're dealing with pH, please always keep 2 to 3 decimal places, and you should keep even more than that on your way to getting the pH. Okay, so that's it for the practice questions there. Again, the most common mistake when doing this is to use your Kb value. Think that you've gotten a concentration of hydronium and plug it directly into a pH formula. So just make sure that if you're dealing with a base or a Kb value, that you don't forget the step of using POH first before finding pH. Okay, so the last thing that we're going to talk about is something called polyprotic acids and polyprotic bases. A polyprotic acid is any acid that contains more than one hydrogen at the beginning. So for example, H3PO4 is polyprotic because of the 3 after the H. H2S would also be polyprotic. So yeah, polyprotic acids are unique because they can react with water more than once to produce hydronium ion. Polyprotic acids are usually not very strong. Usually they don't have very high percent ionizations. And each time they react with water, usually the percent ionization goes down each time. The one exception to that is sulfuric acid, which actually has a really high percent ionization. And then polyprotic bases are just any bases that have more than one hydroxide or that can react to take on more than one H. So that's the type that we're going to be focusing on. Usually these are ions that have charges less than -1. So like a charge of -2 or -3. Because of those -2 or -3 charges, it means they can react with more than one proton and still become neutral. Polyprotic bases also tend to be quite weak because of their low percent ionization. So we're gonna look at some examples of these, but the one thing to note with polyprotic bases is that oftentimes they start off as ionic compounds that first have to dissociate, and then once they are dissociated, one of the ions will have a charge less than -1, which will allow it to become a polyprotic base. So I'm going to flip over to the other camera now and just go through an example of each of these so you guys can kind of see what I'm talking about. Okay, so we're going to start with an example of a polyprotic acid like phosphoric acid. So that's H3PO4. I'm going to show all of the reactions that can possibly happen here. Normally we just go from this right to our phosphate ion, but there's actually a bunch of little steps. So all we're going to do is we're just going to remove one hydrogen ion at a time. So we'll go from H3PO4 to making our H3O+, our hydronium ion, because anytime an acid is in water, it will make a hydronium ion. And then our other ion, instead of just taking all of these acids away at once and saying that we have a PO4 ion left, I'm only going to take one H+ away, and that will leave me with H2PO4-. So I have one less H, and I've lost a plus as well, which is why it's now a negative. I'm then going to take that, and it is going to start my next reaction. So H2PO4- will once again react with water. Because it is still an acid, it still starts with an H. It is going to make a hydronium ion, and then I will take away one more H and one more positive from my starting ions. So it will become HPO4-2. And then I will grab it again, and it's going to start my next reaction. So HPO4-2 can react with water. It still has an H at the front, so it's still going to make H3O+. And then I'm going to take away that last H and make it one more negative. So it'll be PO4-3. I stop as soon as this compound here has no more H's in it. Okay? No H's means I stop. Okay, so each time I'm just removing an H and making it one more negative. If I had just done this as a normal ionization reaction, I would have had H3PO4 plus water becomes hydronium, and take away my H's off the front, PO4, and that's a phosphate ion. It has a charge of 3, which is where this 3H came from. Okay, so what I end up with at the end of all of these reactions is the same ion that I would have ended up with had I just done a normal ionization reaction. I've just shown, instead of removing all of these hydrogens at once, I've just done it one at a time. Okay, let's try a base example now. Okay, so this time we have K2SO4, and I'm going to ask you to show all of the reactions of this as a polyprotic base. But right now, this is just an ionic compound. So my very first step actually has to be to dissociate this into the two different ions. So into the potassium ion and the sulfate ion. Then I can take that sulfate ion, because it has a charge less than -1, and I'm going to react it with water. Because this is a base, it is going to make a hydroxide ion. And because it's a base, it is going to take on a hydrogen. So it's going to become HSO4. And when it takes on that hydrogen, this is really an H plus that it's gaining. So it's going to go from -2 to just -1. Then I'm going to take that again, HSO4 minus. I'm going to react it with water. It's going to make hydroxide. And I'm going to add one more H plus, because again, it's making a hydroxide here. It's acting like a base. So if I add another H plus, it gains an H, and the plus that's added cancels out that minus sign. As soon as I have no more negative charge, no negative, that means I stop. Okay? Now, the one trick is that you might look at this HSO4 minus compound and think it has an H at the front. It is an acid. And you would be right. But because of this minus sign here, it is also a base. Now, if you remember from a couple days ago, we talked about conjugate acid-base pairs. So if I was comparing SO4 minus 2, the one I started with, to the HSO4 minus, this would be a base, and this would be an acid. But if I compare HSO4 minus to what I'm ending up with here, H2SO4, now my H2SO4 is an acid, and the HSO4 minus is a base. Because conjugate acid-base pairs are different by a hydrogen, and the one with more hydrogens is the acid, the one with fewer hydrogens is the base. So HSO4 minus is both an acid and a base. That's why, even though it is an acid, it can still act like a base in this case.